Welcome back to the Neural Intel podcast.
Great to be here.
It is Thursday, February 12th, 2026. And today we are looking at a set of technical specifications that, frankly, they just shouldn't make sense together.
No, they really don't.
Usually, when we get a press release or a new paper, the numbers all line up in a predictable way, bigger models, smarter results, higher costs. It's a straight line.
Right. It's the iron triangle. You pick two.
Today, that equation just completely broke.
It really did. I mean, if you look at the scaling laws we've all been relying on for the last, 5 or 6 years, the Kaplans, the Chinchillas of the world, the numbers we're looking at today are a total anomaly. It feels like a real divergence from just, the brute force method of make it bigger.
We're talking, of course, about the release of MiniMax M2.5. And here is the contradiction, the thing we need to unravel right at the top.
Okay.
We have a model claiming to beat Claude Opus 4.6 on coding benchmarks. That's the current heavyweight champion, right?
Like the undisputed champ.
Yeah. But it's doing it while running on a tiny fraction of the active parameters and costing. It's effectively $0 to run continuously.
It's that impossible triangle of AI engineering we always talk about. Speed, intelligence, and cost.
Right. Pick two.
You get to pick two.
Yeah.
Always. You want it fast and smart. It's going to be expensive. You want it cheap and smart. Well, get ready to wait because it's going to be slow. MiniMax is basically coming out and saying they've solved for all three at the same time.
Exactly. And unlike a lot of the press releases we have to sift through, this isn't just another chatbot update.
Yeah.
The documentation, the blog posts, they explicitly define M2.5 as agent native. And I think we're going to spend a lot of time on that specific phrase today, agent native.
They have to.
Because it implies a fundamental shift in the architecture, not just a bigger data set or a few more training runs.
It implies they stopped trying to build a better conversationalist.
Yeah.
And started trying to build a better worker, a better employee.
So our mission for this deep dive is, I think, pretty clear. We're going to tear down the architecture. We have to look at how on earth they achieved this with only 10 billion activation parameters. That number is just still breaking my brain.
Mine too.
We're going to look at this thing called the Forge framework and some algorithms like CI/SPU that supposedly make it all stable. And then we have to analyze the economics of a model that costs $1 per hour to run at superhuman speeds.
We want to keep this discussion, really rigorous. We're looking at the specs, the architecture, the benchmarks, the community feedback, all of it.
As always, we'll focus on the technical details and implications of the technology we discuss. And to stay updated on all the latest in AI and ML, you can visit our blog at neuralintel.org. And of course, check us out on YouTube, Apple Podcasts, and Spotify.
And we should probably add the usual note.
Right. Just a quick housekeeping note. We are going to be avoiding the ethical considerations or inclusivity discussions. We are here for the engineering, the economics, and the raw performance data. That's the dive.
All right. Let's get into the hook then.
The hook is, without a doubt, the big bomb, as some of the sources are calling it. On February 12th, 2026, that's today, MiniMax officially released M2.5. And the headline claim is just startling.
It is.
Programming power that matches or, in some cases, exceeds Claude Opus 4.6. But here's the kicker, the part that makes you sit up straight.
The money.
The money. The market value of MiniMax has soared beyond 180 billion Hong Kong dollars on this news alone.
That valuation is so significant because it's a validation of a pivot. MiniMax was always seen as a strong player, a solid competitor, but this one release put them in the tier of market shaper.
But what really jumped out at me, even more than the valuation, was the definition. It's that word again. They aren't calling this a chatbot. They aren't even just calling it an LLM.
Oh, the phrasing is so deliberate.
They are officially defining M2.5 as the world's first production-level model designed natively for agent scenarios.
Agent native. We've heard cloud native for, a decade now? Which meant software that was built from the ground up to run in these distributed ephemeral cloud environments.
Wow.
It wasn't just a regular app you lifted and shifted.
Yeah, it assumed a certain kind of infrastructure.
Exactly. And now we're seeing agent native. It implies that the architecture itself isn't just about predicting the next token in a vacuum. It's about predicting the next action in a workflow. It anticipates that it's going to be used in a loop, not just in a chat window.
Okay, let's unpack that. Let's start with segment 1, the architecture of efficiency. I was reading through the technical specs that MiniMax released, and one number just stopped me in my tracks.
I think I know which one.
They list the model as having 10 billion activation parameters.
Right, NB activation parameters.
That just sounds Tiny. I mean, compared to what we assume makes up GPT-5 or Opus 4.6, isn't that incredibly small for a so-called frontier model? I feel like. I feel like I could run a 10B model on my gaming rig at home.
And you probably could,
Hmm.
and that's kind of the point. But we need to be really, really precise here with the language. When they say 10 billion activation parameters, they're not saying the total size of the model is 10 billion.
Okay. So what are they saying?
They are almost certainly referring to a mixture of experts in Mo architecture.
Okay, so break that down for the listeners who might be familiar with the term, but not necessarily the hardware implications of it.
Sure. So imagine you have a massive, massive library full of textbooks. That's your total parameter count. It could be hundreds of billions, maybe even a trillion parameters.
Okay.
That whole library has to sit in the VRAM, the video RAM of your server cluster. And that takes a huge amount of expensive memory. But, and this is the key, for any specific question you ask it, you don't need to read every single book in the library.
Right, okay. If I ask it about Python code, I don't need the model to activate the neurons that are related to, I don't know, 18th century French poetry.
Exactly, you've nailed it. The activation parameters are the number of parameters that actually fire, that actually do the math during a single inference pass. So while the model might have this vast knowledge base sitting there sort of at rest in memory, it only activates a slice of it, in this case 10 billion parameters, to generate a specific token.
So it's basically efficiency through specialization. It's not firing every neuron in its brain for every single thought.
Correct. But, and this is the technical trade-off that people often miss with MOE.
Okay.
MOE models save on compute. They save on the FLOPS, the floating point operations per second, because you're just doing less math per token. But they do not save on memory bandwidth.
Ah, because you still have to keep that whole library loaded in VRAM.
You have to keep the whole library loaded, and more importantly, you have to be able to pull the right book off the shelf, like instantly.
Right.
That requires massive memory bandwidth. So the fact that MiniMax got the activation parameters down to 10B while maintaining this frontier-level intelligence, it suggests their router, the part of the network that decides which experts to use for which problem, is incredibly, incredibly efficient.
So the router almost never makes a mistake. It knows exactly which expert to call on.
That's the implication. If the router picks the wrong expert, it sends your Python coding problem to the French poetry expert, the output is complete garbage. So a low activation count combined with high performance is really a testament to the accuracy of that routing mechanism.
Now, there's a really fascinating nuance here that I was digging into regarding the underlying attention mechanism. I was looking at a discussion on Reddit, specifically from a user named DistinctTarget7503.
Oh, yeah.
And they noted something really technical about how the MiniMax architecture has evolved over time.
This is a great catch by the community. What did they find?
They pointed out that MiniMax previously used a hybrid architecture in their older models, like the O1 and M1. And hybrid usually means mixing transformers with something else, like an RNN or a state space model.
Right, things with linear attention designed for, like, infinite context.
Exactly. But for the M2 series, including this new M2.5, they've actually moved back to classic attention.
See, that is super counterintuitive. The whole industry has been screaming about linear attention for years because it's so much cheaper on memory. It's what allows you to have a 1,000,000 token context window without your VRAM just exploding.
So why go back? I mean, isn't that a regression? It sounds like a step backward.
It's a trade-off. It's always a trade-off. Linear attention is really efficient, but it's also lossy. It approximates the relationship between all the tokens.
Okay, what does lossy mean in practice?
It means it struggles with what we call the needle in a haystack problem. If you give an agent a massive 100,000-line code base and ask it to find one specific variable definition on line 73,421, linear attention might just blur over it.
So it gets the gist of the document, but it misses the tiny critical detail.
Exactly. It's like a blurry photo. You can see the scene, but you can't read the license plate. And for a coding agent, which is exactly what M2.5 claims to be, you can't have blurry vision. You can't hallucinate a variable name. You need 100% perfect recall.
So MiniMax made a conscious decision. They realized that for a coding agent, accuracy is completely non-negotiable.
Right. So they went back to the expensive architecture classic attention because it offers that perfect mathematical precision. But then they solved the cost problem from a different angle, using this extreme MOE sparsity we just talked about.
Wow.
That's a really pragmatic engineering choice. It's like they said, okay, we will pay the high cost for perfect attention, but we will save all that money on the feed-forward networks by using this hyper-efficient MOE setup.
And they certainly seem to have solved the speed problem, too. The specs list the throughput at 100 TPS. That's 100 tokens per second.
Which is just blistering. For a model that's performing at the frontier level, that is incredibly fast.
It's nearly twice the speed of other frontier models, like what we see from GPT-4 or Opus. But let me ask you this. Why is that specific speed 100 TPS so critical for an agent model? I mean, who cares if it writes fast? Is it just about user experience?
It's way more than that. Think about how an agent actually thinks.
Okay.
It doesn't just answer a question and stop. It loops. It makes a plan. It critiques its own plan. It decides to try a tool. The tool fails. It reads the error message. It revises the plan, and it tries again. That whole process is a loop.
Right, it's an internal monologue.
Exactly. And if you're running at, say, 20 tokens per second, which is still pretty good for a big model, that loop can take minutes. The user gets bored, the system times out, but more importantly, the latency just kills the utility of the agent itself. At 100 TPS, the agent can have that internal monologue, self-correct multiple times, and execute a complex, multi-step piece of reasoning in the time it takes a normal model to just, clear its throat and start typing.
So it's the difference between a sluggish employee who takes a whole week to finish a complex task and one who just sprints through it in an hour.
Precisely. High throughput isn't a luxury for agents. It's a fundamental structural requirement for any kind of effective agentic behavior. You simply cannot have useful agents without high speed. It's a non-starter.
Okay, this is fascinating. I want to drill deeper into how they actually achieved this stability and the training speed they're claiming. This feels like the perfect time for our neural signal check.
Let's do it.
Neural signal check. Here's why this development actually matters at a deep technical level. We are looking at a framework the sources mentioned called Forge.
Yeah, Forge is the secret sauce here. From everything I can gather, it's an agent-native reinforcement learning framework that they've developed entirely in-house at MiniMax.
The source material mentions that Forge decouples the underlying training inference engine from the agent. But that sounds like a lot of jargon soup. What does that actually mean for an engineer?
Okay, think of it like this. In most traditional training pipelines, your model and the environment it's interacting with are sort of mashed together. They're tightly coupled.
Okay.
So if you want to train the model to use, say, a calculator tool, you have to hard code that interaction into the training loop. Then, if you want to switch to a Python interpreter tool, you have to go back and rebuild significant parts of the pipeline.
So it's rigid. Every new tool is a major engineering project.
It's extremely rigid. Forge acts as a middleware layer, an abstraction layer. It creates a clean separation between the brain, the model, and the hands, the tools.
Oh, okay.
This allows MiniMax to plug in what they call arbitrary agents. They can swap out the tools, the scaffolding, the environment, without having to fundamentally rebuild that core training engine every single time.
So they can train it on coding in the morning, web browsing in the afternoon, and Excel spreadsheets at night, all using the exact same core optimization engine.
Yes, that's the dream. It allows them to optimize for generalization across a huge variety of different tools. It's basically modularity, but applied to the training process itself, which is a really big deal.
And within this Forge framework, they're using some very specific algorithms. The source mentions one called CISPO.
CISPO.
Right.
That stands for a constraint-based optimization algorithm they proposed, I think, early last year. And its main job is one thing: stability.
And stability is a massive issue with these big MOE models, isn't it?
It's huge. It's one of the main reasons they're so hard to work with. When you're training these massive mixture of experts models using reinforcement learning, things can get really volatile really fast.
How so?
Well, you have all these different experts learning different things at different rates, and sometimes you get a problem called expert collapse.
Expert collapse? What's that?
It's where the router, the part that directs traffic,
Yeah.
gets lazy. It finds one expert that's pretty good at most things, and it just starts sending everything to that one expert.
So your mixture of experts becomes a mixture of one expert?
Exactly. The whole model just collapses into a single non-specialized model, and you lose all the benefits of the MOE architecture. CISPO works by applying these clever mathematical constraints to the policy updates to keep the MOE stable. It basically forces the experts to stay diverse and balanced during these massive training runs.
And what about this other thing they mention, a tree-structured merging strategy?
Ah, yeah. This is the efficiency hack. This is where the crazy speedup comes from. They're claiming a 40x training speedup with this.
40 times!
It's insane. So instead of training on these long linear sequences of data, point A to point B to point C, they structure the training samples in a tree format.
Like a decision tree? Is that the right analogy?
It's a similar concept, yeah. It likely groups similar reasoning paths or branching possibilities together in the data. This allows the model to learn from multiple potential outcomes simultaneously, in parallel, rather than having to process them all one by one sequentially.
A 40x speedup is it's a game changer. That explains how they're iterating so incredibly fast on this stuff.
It does. It essentially means they can run 40 experiments in the time it takes a competitor to run one. And that's a compounding advantage. If your iteration cycle is measured in days instead of months, you win.
So we have this blisteringly fast, hyper-efficient architecture, but what can it actually do with all that power? Let's move to segment 2, the spec writing coder.
This is where the rubber meets the road, right? Coding is, right now, the killer app for LLMs. If you can code, you can build tools. And if you can build tools, you can pretty much do anything.
The claims here are incredibly bold. They are claiming state-of-the-art SOTA performance in coding and agentic tool use. Let's just look at the raw benchmarks. SWE bench verified, 80.2%.
And just for context, that matches or even slightly exceeds Claude Opus 4.6, which, as you said, has been the gold standard for months now. Getting over 80% on SWE bench verified is basically the entry requirement for the elite club of coding models right now.
And multi-SW bench is at 51.3%. But, numbers are just numbers. What I found really fascinating was in the MiniMax blog post, where they described how M2.5 codes, they call it a spec writing tendency.
Yeah, this is such a key qualitative difference. Most models, when you ask them to build an app, they just start spitting out code immediately.
Right.
Here is your Python script. They're just mimicking the autocomplete behavior they were trained on for so long.
Right. They're just guessing the next most likely word or token.
But M2.5 has been trained, likely, through that very sophisticated reinforcement learning process we just discussed, to act like a software architect first. It actually pauses.
So it generates a plan, a specification, before it generates a single line of code.
Effectively, yes. It decomposes the problem. It structures the whole project. It designs the UI in its head, or specifically in its output plan, before it writes a single line of executable code.
That is exactly what a senior engineer would tell a junior engineer to do. Stop. Don't just start typing. Plan it out on the whiteboard first.
Exactly. It's like a structural built-in chain of thought. And the source describes it as covering the full life cycle. The 0 to 1 initial design, the 1 to 10 development, and even the 90 to 100 testing and review phases. So it's not just a code generator, it's being pitched as a project manager that also happens to code.
Okay, this sounds absolutely fantastic, but I have to play devil's advocate here. Is this just marketing fluff? How does it perform in the real world? I want to bring in some boots on the ground data here. We have a source from Reddit, user Lemon07, who runs the Sanity Board benchmarks.
Ah, yes, Lemon07 are legend in the local LLM community for doing these really rigorous independent tests. And their findings are, well, they're nuanced.
Okay, what did they find?
So first, the good news for MiniMax. When M2.5 is combined with something called the droid-agent combo, which is a specific agentic framework, it apparently dethrones the previous open-weight king, which was Kimi K2.5. It actually takes the crown for best performance in that specific setup.
Okay, so the potential is real. When it works, it really works.
The potential is definitely real. But, and this is a big but, here's a catch. Lemon07R notes that MiniMax is highly, highly sensitive to the agent environment it's placed in.
And sensitive how, exactly?
If you put it in that droid environment, it's elite, world-class.
Yeah.
But if you put it in a different, more generic harness, its performance drops off a cliff. It actually performs poorly.
Huh.
Now, you compare that to Claude Opus. Opus is described as being agent agnostic.
Mm-hmm.
You can throw Opus into almost any scaffolding, any framework, and it just sort of figures it out. It's robust.
So MiniMax M2.5 is a bit of a diva.
Shuckles. That's actually a great way to put it, yeah. It's a virtuoso, but it demands a very specific stage, a specific orchestra.
That is a crucial distinction for developers, isn't it? It means M2.5 isn't just a simple drop-in replacement for everything. You have to build the right system around it to get that SOTA performance?
Correct.
Yeah.
It implies that their agent-native claim is true, but it also means it expects an agent-native environment to work in. It expects tools to be presented in a certain way. If you don't speak its language, if you don't let it do that spec writing routine it's been trained on, it just doesn't shine.
The source also mentions the language support. It's not just, Python and JavaScript.
No, it's broad. They list over 10 languages, including Go, Rust, C++, DOS, and TypeScript. And they say it's been tested on over 200,000 real-world environments. That sheer volume of testing suggests they weren't just looking for simple syntax errors, they were looking for deep logical errors in complex real-world systems.
Which brings us right back to that architecture. It plans, it codes, it tests. But how did it get so good at the process? MiniMax says it's all about the reinforcement learning. So let's move to segment 3, reinforcement learning and the professional employee.
This is the scale story, but a different kind of scale. We usually talk about scaling laws for parameters, just make the model bigger. MiniMax is talking about the scaling of reinforcement learning.
They mentioned turning hundreds of thousands of their own internal tasks into training environments.
And that is the key. That's the alpha right there. They aren't just scraping GitHub and Stack Overflow like everyone else. They are taking actual tasks, internal workflows, bug reports, feature requests, and turning them into RL gymnasiums for the model to train in.
And there's a specific technical nuance here, too, regarding how they reward the model. They use a process reward mechanism.
Yes, and this is designed to address the infamous credit assignment challenge.
Okay, let's do a quick neural signal check here. Break down the credit assignment challenge for us.
Okay, imagine you're an AI agent. You have a task that takes 50 steps to complete. At step 50, you succeed. Great, but which of the previous 49 steps was the most important one? Was it step 3 where you chose to import the right library? Was it step 12 where you correctly identified and fixed a subtle bug? Or was step 49 the only one that really mattered?
So if you only give the reward at the very end, at step 50, the model takes a really long time to learn how it actually succeeded. It doesn't know which part of the process was good.
Exactly. That is the credit assignment problem in a nutshell. In these long horizon tasks, sparse rewards, where you only reward the final result, are incredibly inefficient for training. A process reward mechanism does what it says. It rewards the model along the way, throughout the process.
So it's like a teacher who grades your math homework step by step, giving you points for showing your work rather than just checking if the final answer is right.
It's the perfect analogy. It monitors the quality of the generation end to end. Good job on step 5. Hey, that was a mistake on step 10. It provides this incredibly granular feedback, which is absolutely essential for teaching these complex, long-context agentic tasks.
And they're applying this beyond just code. They are explicitly calling it office work.
This is where they're clearly trying to capture the enterprise market. The sources say they collaborated directly with experts in finance, law, and social sciences.
I love this phrase they use. They're trying to build tacit knowledge into the pipeline. Tacit knowledge.
It's such a great phrase. It's the difference between knowing the dictionary definition of a financial hedge and knowing how a real risk manager actually constructs one in a messy, real-world Excel sheet. It's all the unwritten rules of a profession.
They give some specific examples. For Microsoft Word, they say it doesn't just generate text. It follows research framework SOP standard operating procedures.
Right. And for Excel, it's not just about spitting out the right formulas. It's about following risk control logic. It's simulating a trained professional employee, not just a fancy calculator. It knows that certain cells shouldn't be hard-coded. It knows how to structure a pivot table for maximum readability by a human manager.
And they are really, really eating their own dog food here.
Oh, heavily. They claim 30% of MiniMax's own internal tasks are now completed by M2.5. And this next stat just blew my mind.
The coding one.
80% of new code written at MiniMax is generated by M2.5.
If that number is even close to true, that represents a singularity moment for their internal development team. They're not developers anymore. They're essentially managers of the AI that writes the software for them.
It's recursion. The AI is building the next version of the AI. And because it understands that spec writing process we talked about, it's likely generating cleaner, better documented, more maintainable code than the humans were.
Now, all of this performance is incredible, but usually performance comes with a hefty price tag. You want the Ferrari, you pay for the Ferrari. But Segment 4 suggests MiniMax is trying to completely break that rule. Segment 4, the economics of intelligence too cheap to meter.
This is arguably the most disruptive part of the entire announcement. I mean, forget the benchmarks for a second. Just look at the wallet.
Let's talk about the $1 statistic.
It's so simple and so powerful. Running M2.5 continuously for 1 full hour at that blistering 100 tokens per second speed costs $1.
$1 for an hour of continuous superhuman-level code generation and architectural planning.
And it gets crazier. If you drop the speed to a still very fast 50 TPS, the price drops to 30 cents per hour.
That's practically free. It's a rounding error.
It is. The blog post puts it in perspective. The output price is 1/10 to 1/20th of Opus, Gemini 3 Pro, and GPT-5, a full order of magnitude cheaper.
They have this visualization in their post that really drives the point home. You can run 4 M2.5 instances continuously, 247 for an entire year, for a total cost of $10,000.
For a large enterprise, $10,000 is nothing. That is less than the cost of a single junior intern for one summer.
But here's the question, and this feels like another neural signal check moment. Why does this cost matter technically? Not just financially, but technically. Why should an engineer care so much about the price?
Because cost dictates architecture, period.
How so? Explain that.
If intelligence is expensive, like GPT-4 was when it first launched, costing a fortune per API call, you optimize your software to minimize those calls.
Right.
You spend weeks on careful prompt engineering to try and get the perfect answer in one single shot. You are scared to let the model loop. You treat the model like a high-priced consultant that you only call in for 5 minutes.
Right. You don't want to rack up the bill by letting it just sit there and think.
But if intelligence is cheap, if it's effectively free, you can afford to be inefficient. You could afford what the researchers call inference scaling.
You can just let the agent spin its wheels until it gets it right.
Exactly. You can design an agent loop that critiques its own work 50 times before it shows you the final answer. You can have it generate 20 different variations of a user interface and then have another agent pick the best one and discard the other 19. You can have it think for 10 straight minutes before answering a complex question.
This sounds a lot like System 2 thinking, the slow, deliberate reasoning.
It is exactly that. When the cost of a thought approaches zero, the entire software architecture shifts from being one-shot to many-shot, or even infinite loop. You move from building a query engine to building a true reasoning engine.
The source quotes MiniMax saying this is the first frontier model where users do not need to worry about cost. That single statement frees up developers to build things that were previously economically impossible just a year ago.
It enables brute force reasoning. If the model is stuck on a really tricky coding problem, who cares? Just let it try 500 different solutions. It costs you a nickel.
The reaction on Reddit to this pricing was, as you can imagine, just wild. A user named Jamooz just flat out called it a game changer.
And user Edzomatic did the math and broke down the token costs. Input is 0.3 per million tokens. Output is 1.2 per million. And this is the really interesting part. Cached input is 0.03 per million.
0.03 per million for cached input. So if you're feeding it a massive code base as context, you pay almost nothing to keep that context load after the first time.
Correct. It's a massive incentive to use huge context windows. It encourages you to just dump your entire code repository into the prompt and just leave it there for the whole session.
But there was, of course, a comparison to DeepSeek.
Always. DeepSeek has been the undisputed benchmark for value for a while. And the users noted that M2.5 might still be slightly more expensive token for token than DeepSeek's latest V3 model or something similar. But the argument is that M2.5 offers fundamentally different capabilities.
Specifically that agentic spec writing capability we keep coming back to.
Right. DeepSeek is an amazing model, but is it a spec writer? Is it an architect? That seems to be the differentiator MiniMax is pushing. They're claiming you get premium Opus-level intelligence, but at commodity prices. Whereas DeepSeek has been more in the category of great intelligence for the price. It's a subtle but important distinction.
Okay, let's zoom out a bit. Segment 5, the market landscape and the open debate. The release happened today, February 12th, 2026. The market absolutely loved it.
Oh yeah. Share price shot up 20%. Market value is over 180 billion Hong Kong dollars. They're firmly in the big league now, competing for that top AI stock title against companies like Zhipu.
But while the investors are, popping champagne, the developers over on Reddit, specifically in the R-Local-Llama community, are having a bit of a spirited debate.
It's the classic, is it really open source controversy.
Is it open or isn't it? What's the verdict?
Well, therein lies the confusion. The official announcement says it's officially released. Now, to a suit, to an investor, that means great, you can buy the API. But to a hacker on R-Local-Llama, released means, where are the weights? Can I download this to my own GPU right now?
And the answer to that question is?
Currently, it's available via their API and something called a coding plan. But the local runners, the people who want to run it on their own hardware, are still waiting for the weights to drop on a Hugging Face.
User No Conversation 9561 pointed out a historical trend here that might be relevant.
Yeah, that was a good point. They noted that MiniMax's previous model, the M2.1, took a full month to release its weights after the API was announced. And you can contrast that with a company like GLM, another big Chinese lab, which usually releases its weights immediately. So the community is, understandably, a bit skeptical. They're asking, is this truly open, or are you just teasing us to build hype for the API?
It's that whole open weights versus open source versus open API dance we see all the time.
And until those weights are on Hugging Face, and people can verify these 10B activation parameter claims and the performance on their own hardware, the local community is going to remain cautious.
And the comparisons are just flying. GLM5 versus M2.5 versus Kimi. It's a three-way battle.
Yeah, some users are already claiming that GLM5 won't take off in the local community if these M2.5 benchmarks hold up once the weights are released.
That is a pretty brutal assessment.
It's a winner-take-all market for developer attention and mindshare. If M2.5 is genuinely faster and that 100 TPS is a huge draw and smarter on code, users will absolutely switch.
There was that specific speed comparison to Claude Opus 4.6 on the SWE bench verified test.
Right. M2.5 finished the benchmark task in 22.8 minutes. Opus took 31.3 minutes.
So it's a full 37% faster.
And remember, in the world of CI/CD pipelines and developer workflows, time is money. But more importantly, time is latency. If I'm a developer waiting for an AI to fix my code, a 10-minute difference is a lifetime.
So we basically have this massive battle shaping up for the cheap range of models. You've got Kimi, DeepSeek, and now MiniMax all fighting for that coveted $1 per hour crown, while Opus and GPT are still sitting up at that high-cost premium tier.
It really feels like the market is bifurcating. You have commodity intelligence and premium intelligence. But MiniMax is the one claiming to have broken that divide. They're claiming premium intelligence at commodity prices, and that's the real disruption. If they can actually deliver Opus-level logic for $1, the whole high-end market could just collapse.
Before we wrap up, we should probably look at the broader context. Let's do segment 6. It's February 12, 2026, and MiniMax wasn't the only piece of news that dropped today.
No, it was actually a really busy news day for AI.
Google launched something called WebUXL.
Right, which is a big African speech data set covering 21 languages. And this is relevant because it ties into the theme of data sovereignty. It's a move to ensure that African data ownership remains with local institutions. It just highlights that while we talk about this global AI race, the actual data layer is becoming increasingly nationalized and sovereign.
And then there was Xiaomi, the phone company.
Xiaomi Robotics Zero, a 4.7 billion parameter robot model.
A robot VLA model. What does VLA stand for?
Vision Language Action.
Ah, okay. Makes sense.
It's a model designed specifically to solve the collaboration problem between the brain of a robot, the high-level planning, and the cerebellum, the low-level motor control.
Why does that matter in the context of our discussion about MiniMax?
It connects directly to the agent theme. MiniMax M2.5 is a software agent. It's designed to move bits around. Xiaomi is building a hardware agent, a robot designed to move atoms around. But the underlying trend is exactly the same, specialization. We aren't just seeing generic chatbots anymore. We're seeing coding agents, robotics agents,
and video agents. Speaking of which, ByteDance also released Seedance 2.0 today.
A unified multimodal architecture for video generation. Again, specialized efficiency. The entire industry seems to be moving away from the one model to rule them all paradigm and shifting towards these highly efficient specialized models designed for specific high-value economic tasks.
Which brings us nicely to the outro.
Let's try and synthesize all this.
Okay, MiniMax M2.5. The big takeaway is that it represents a clear shift to what they're calling agent-native design.
Yeah, the key takeaways for me are clear. High throughput, that 100 TPS is the new speed limit to aim for. Low activation parameters 10B is the new efficiency standard, and it's achieved using MoE. Massive RL scaling, turning your own office into a training gym via frameworks like Forge. And finally, a cost structure, $1 per hour, that fundamentally changes the economics of automated labor.
It encourages continuous agent operation. You don't turn it off between tasks. You let it run.
And that leads me to a final question, a provocative thought for our listeners to chew on.
Go for it.
The sources mention this repeatedly, that M2.5 has a spec writing tendency. It plans before it acts. It behaves like a software architect.
Right.
So if these models are now the architects and not just the bricklayers, and the cost of hiring that architect is approaching zero, what happens to the human junior developer or junior analyst?
You mean what happens to the entry-level jobs?
I don't even mean ethically. We promised we wouldn't go there. I mean structurally. From an engineering perspective, how does the code base itself change?
That's a really fascinating angle. I hadn't thought of that.
If a machine is designing the system from the ground up, and that machine thinks in 100 TPS loops, and it self-corrects its own plan 50 times a second.
Hmm.
Does the resulting software architecture become something that we humans can even understand anymore?
Wow. You mean, does the code it writes become alien?
Exactly.
Hmm.
Does the code base become so hyper-optimized for agentic maintenance that a human junior dev looking at it for the first time literally cannot parse the logic? Are we on the verge of building software that only other software can read and maintain?
That is simultaneously a little terrifying and also very, very exciting.
It's the ultimate black box, not the AI model itself,
Hmm.
but the product created by the model.
Wow. Okay, listeners, that is your homework for the week. We absolutely want to hear from you on this. Do you trust a model that plans your software architecture before it writes it? And more importantly, are you ready to debug code written by a machine that thinks 100 times faster than you do?
Let us know what you think in the comments.
As always, you can check out the full technical breakdown and links to the sources on neuralintel.org. We will be back next week, and hopefully by then we'll have those M2.5 weights finally on Hugging Face. We can test it ourselves.
Fingers crossed for that.
This is Neural Intel, signing off.